Good afternoon, everyone, and thank you for joining us. Today, Benjamin,
Hello, I'm Benjamin.
Natalie,
My name is Natalie Mendoza.
and myself will be discussing Nexus' new breakthrough healthcare product line, Grand Connections, bringing affordable at-home healthcare to the elderly. Many families struggle to afford full-time care for their elderly family members, so we here at Nexus developed an automated team to fill that need. It can be deployed in both homes and healthcare facilities. Now you have a cost-effective, reliable, and technologically savvy machine to help facilitate care. Our direct customers include the individuals caring for geriatric patients. The main goal is to provide aid, whether that be to struggling families who may not have the opportunity to visit frequently, or to medical facilities such as nursing homes and hospitals who are experiencing staffing shortages. Indirect customers include patients, family members, and medical professionals. In our research, we observed some overlap between direct and indirect customers through families. Depending on the specific role in the family dynamic, individuals may serve as caretakers, which is more direct, or supportive loved ones, which is more indirect. Medical professionals will benefit from the additional support, while family members take comfort in knowing that their loved ones are safe. Additionally, taxpayers may be impacted by the robot swarm's costs if covered by Medicaid or Medicare. The design requirements for this swarm include determining the time of day and allowing for external communication from patients to families to medical professionals and emergency services. The design must maintain internal communication with the remaining robots in the swarm. It must also be waterproof, dustproof, and withstand general wear and tear. The design must also be able to connect to smart devices. The design must perform self-diagnosis to maintain care and safety, and be operable for a minimum of 48 hours without external power. Lastly, the design must maintain at least one active robot at any given time. Moving into individual robots, we have the well-being robot, which monitors overall health and well-being of patients. The household chores robot, which manages the daily upkeep of the patient's living quarters, and the medical care robot, which provides first aid emergency medical care to the patients.
Today I'm going to introduce you to the General Well-Being Robot. Standing at 3 feet tall and 1 foot in diameter, this little beauty serves to observe the patient. This entire model has been designed around that function. Firstly, it was designed with a minimal amount of moving parts. That, coupled with solar power, will keep this running indefinitely. In the event power can't be found, it also comes with a plug. During iteration, I decided to make the arm completely stationary. Since the General Well-Being Robot is an observe and report as its primary function, the arm motor was instead repurposed to serve as a servo motor for the dispenser. The large ball and spring provide omnidirectional movement, and with a little help, how level the ground is. As you can see from this flowchart, most of my robot's primary function is to monitor and report. After initializing the variables, it asks a series of questions. Since the patient is the primary focus, we want to check if the patient is moving. After that, the questions are, has the patient had their meds? Has a medical care robot been deployed? Has a household chores robot been deployed? And has it started its rove? Each of these questions are the key to unlock further response. Since communication is a main function, the void loop only serves to initiate the other functions. Everything interesting happens behind the scenes. Since visually checking movement is outside the scope of the current prototype, I use a simple motion sensor to check if the patient is moving. If so, the forward function is called. This function recursively checks the position of obstacles and rotates the motors according to the positioning needs. Here we get into the nitty-gritty of the code. Each code block here is a contained function. The serial.print, serial.readString, and serial.parseInt portions simulate the input received or being sent. The parseInt portions take 1 or 0 to simulate a true or false boolean being received.
Household chores robot. The household chores robot is 1.5 feet long by 1.5 feet wide by 4 feet tall. It is sitting upon a wireless charging station, also known as a dock. This design includes lateral rotation of the head up to 180 degrees, shoulder abduction and flexion of 180 degrees, elbow flexion of 140, and wrist flexion of 90 degrees. The hands also have 90 degrees and range of motion. From top to bottom, this robot contains one ultrasonic distance sensor for navigation and obstacle detection, one infrared scanner for sight, 7 servo motors for the neck and arm movements, one DC gear motor for piston control. This will allow the robot to adapt to its environment by adjusting its height to a maximum of 5 feet, and one hobby gear motor to control the tread, which allows for movement. Some key features in the household robot include fully articulate arms and semi-articulate hands, extendable torso, good range of motion in the neck, and customizable colors. Due to the number of motors and actuators in the household chores robot, the circuits have been divided up to clearly show each one. Starting with the head and body, from left to right, top to bottom, we have the ultrasonic distance sensor, infrared scanner, gear motor, DC piston controller, and the servo motor. And in the arms, we have 4 servo motors, which represent the shoulder that goes up and down, elbow that goes up and down and side to side, and one to open and close the hands. The first thing the robot does is perform a scan to make sure it can see and there are no obstacles nearby. Next, if pinged, it will go to the location of the ping and perform the appropriate cleaning task. If it hasn't been pinged, it will go on a rove. Any discrepancies will be cleared immediately, and it will return to the dock upon completion to idle until its next rove in 30 minutes. Going into our Arduino code, we can see that for the head and body circuit, we declared our variables, set their input and outputs, and then coded everything for all head rotation, object sensing, piston extension, and tread movement. For the arms, we can see shoulder movement up and down, elbow movements up and down, and right and left, and the opening and closing of the hand.
We are going to start off our demonstration by having our robot look around. So, neck left will cause the servo motor at the bottom to look to the left, and neck right will cause him to look to the right. You can also see our piston motor, which is going to be at the bottom. If we say blocked, it'll turn on to adjust the piston, and then turn off. Piston back down. And then up here, for our distance sensor, if we are closer than 10 inches, it will stop and stop rolling. But as soon as we have clearance, it'll keep going. For the arms, we have a similar situation. This is the shoulder, this is the elbow up and down, elbow left and right, and then this is the hand. So if we say arm up, it will raise the arm up. And same thing for arm down. Elbow up and elbow down. Elbow to the left, and then elbow to the right. And then hand close, we'll close the hand, and then hand open. We'll open the hand.
I designed the medical care robot. The medical care robot is composed of a rectangular body, a long flexible arm, 2 spherical wheels, 3 sensors, 2 actuators, and a sensor tray controlled by pulleys. The robot has 2 actuators, microservos, that control its motion. Additionally, the robot uses multiple sensors to detect if the patient is breathing or bleeding, as well as how much pressure the robot is exerting on the patient while applying a bandage. I replaced the original piezo sensor with a gas sensor because ensuring respiration is more important to patient health than taking an ultrasound. This robot is idle until it receives an input from the general well-being robot. Upon receiving an input, the robot moves to the patient's location, checks if the patient is breathing or bleeding, and responds based on that information. The Arduino code programs the servo motors, the sensors, and the communication features of this robot. When the gas sensor does not detect a value greater than or equal to 300, the robot calls 911 and turns on its yellow LED. Otherwise, the robot checks if the patient is bleeding using a moisture sensor. If the patient is bleeding, the positional servo motor starts rotating and the force sensor slowly increases as the positional servo motor moves the arm to apply a bandage. When the force sensor reaches a value of 600, the positional servo motor returns to its resting state. To signal completion, the red LED flashes repeatedly. This flowchart shows the collective behavior of the robot swarm. The general well-being robot acts as the central hub. The general well-being robot messages the medical care robot when the patient is on the ground, and the household chores robot when there is a hazard on the floor. Both the medical care robot and the household chores robot also communicate with the general well-being robot to indicate task completion.
Hi, me again. I'm here to talk about the most important part of our project, the money. When it comes to a real-world product like this, we need to think about the material costs. If we don't know, we estimate. Since materials make up approximately 30 to 40% of the robot, it was decided to measure the mass of a box that matches the dimensions of each robot. That mass was then converted to kilograms and multiplied by the cost of each material. The casing takes 20% of that mass and then applies that to fiberglass. Frame estimates include $1,049 for manufacturing costs. These estimates are done like this to leave room for component purchases. Robots have already started to be introduced into the medical field. Moxie is a robot in Michigan that helps at hospitals. There are also whispers of products planned for home health care. There's a smart clothing line in place to monitor a patient's temperature, medical machines designed compact enough to be used in a home setting, and apps to perform tests on a patient at a home level, just to name a few. So, if that's the case, what is the need for our product? Each of these proposed products lacks one key thing. They collect information, but there is no action. If an alarming drop in temperature happens, how soon can a patient receive assistance? If the heart monitor or test notes an alarming thing, how is it stored? I am sure Moxie should be able to address some of these concerns, but it also has a flaw. It is designed for hospitals. Enter Grand Connection. We are designed for the home. The patient doesn't live in the hospital, so information and care should be where they primarily reside, at home. Each of the materials we price are also there to allow for customization for the customer. So, what will it cost you? Each unit will run you just shy of $33.5 thousand. Yearly, however, includes a monthly $2,000 subscription. This allows us to maintain the database. This means home health care at less than 10% of existing costs. During this, our team learned a lot about an entrepreneurial mindset. We learned to tailor a solution to a customer, how to set up visuals for presentations, and how to arrange our information in an advertising manner. It was especially an interesting challenge to apply these concepts to engineering, as well as coding them in Arduino.
Our team learned multiple lessons about good management skills, including how to use a Gantt chart to stay organized and plan a project, how to step back and allow things to progress naturally, and how to work together to stay ahead and alleviate stress. If we did this project again, we would have printed 3D models of our robots, added additional sensors to improve patient care with more features, tested the robots using physical components, and simulated the robot swarm's collective behavior in MATLAB. Competitively priced robot swarm that provides in-home care to elderly patients. Each robot in this swarm is responsible for a specific aspect of patient care. The general well-being robot manages medication and acts like a central hub. The household chores robot performs chores, and the medical care robot treats the patient after a fall. This robot swarm fills a gap at in-home patient care for aging individuals. Thank you.